Okay, Bobcats, this is Organic Chemistry 2341, Chapter 9, the last section, which is mass spectrometry. Okay, so to introduce mass spectrometry, we actually take a small amount of a compound and we vaporize it into the vapor phase, and then we ionize it. Typically, we remove an electron, making it have a radical cation. Okay, when we do that, the molecule that we've only removed an electron from becomes our molecular ion peak. Okay, and so we can sense that by how large that ion is because they're separated by molecular mass. Okay, so the energy of the ion beam also starts to break that molecular ion into smaller fragments of radicals and cations and neutral species. Now, the way in which they break is based on how stable the different fragments are. And so we'll see different fragments break off from different types of materials. Okay. Now, and it's good to note here that we only see cations in the system. We see radical cations and cations in the system. We do not see uncharged species in our mass spectrometry. Okay. So one of the great things about mass spectrometry is it's unique for each compound because each compound breaks apart in a different way and has relative abundances of different bonds, etc. That means that we can get like a fingerprint, like in the fingerprint region of IR, and we can positively identify our compound just by its mass spec. And the reason we can do that is there's four things that determine the spectrum we get from our molecular spectroscopy. Okay, number one is the molecular ion peak, which tends to get the molecular weight of the anion because it's just the radical cation of the molecular ion. Okay, so we haven't taken off any mass, so that gives us the molecular ion peak. Then we have the base peak, which would be the tallest peak in our spectrum, and that tends to be the most stable fragment because our molecular ion typically is not very stable, will break apart, and that first break apart will give us the most stable fragment, and that's going to give us the highest abundance of that, and that counts as our peak, our base peak. Okay. Now, all the other fragments are based on their relative abundance based on the base peak. Our base peak is typically about 100%, and all the other fragments are given a percentage of that, okay? Now, the last thing we look at is the fragmentation pattern. If you have like a carbon chain, you're gonna see a carbon and two hydrogens break off, and as you go down the chain. And so the fragmentation pattern you get tells you a lot about how the molecule is hooked together. All right, let's look at some other things associated with this. All right, so let's start with just the fragmentation of pentane. And we are sharing, share with me, please. There we go. All right, so let's talk about the fragmentation of pentane first. Okay, so pentane has a molecular weight of approximately 72. Okay, so our molecular ion peak is going to be the highest mass peak we see, and that is going to be our 72 molecular weight, and therefore we see that as the highest peak here. However, that's not the most stable fragment we produce. The most stable fragment we produce here is the propyl, or the 3-carbon group here, 3 carbons here, or the molecular weight of 43. So that becomes, because that's our most stable fragment, it is also our base peak, okay? So the other thing to note is looking at our fragmentation pattern. We start from 72 and we lose 15. 15 is a CH3 group, or a methyl group. The next thing we see is the loss of 29. That's an ethyl group. Okay, so if you drop an ethyl group off either side, you get to this base peak here. And then this is the appearance of your ethyl peaks, and then this is the appearance of your methyl. Okay, so we have our molecular ion peak, the loss of a methyl, the loss of an ethyl, our ethyl, and our methyl peaks, all showing up in our fragmentation pattern of a straight chain hydrocarbon. So imagine that you have a tertiary carbon here. That's going to give you a more stable carbocation, and therefore you're going to see that as a bigger base peak than some of the other fragmentation periods. So we have to think about that. That pattern we see, it is an indication of what kind of linkages we have, and therefore that fragmentation pattern is unique for each type of compound. Okay, so let's look into that fragmentation pattern in a little more detail here. So we start with our molecular ion peak, and our molecular ion peak is always done mass per unit charge, or M over Z. Now, most of the time our molecular ion peaks have a single cation on them, and so we have our molecular ion divided by 1, which is our charge species here. Okay, so once we form that molecular ion, or that radical cation here, it can break apart into a couple different things. It can break into a radical and a cation, giving us our base peak of 43. It can also break into a cation and a radical, which would also give us our base peak of 43. However, it's not charged. So we don't see this because it doesn't have a charge on it, but we do see this peak because it does have a positive charge on it. Okay, so it can also break off with just a methyl group. So we see a loss of 15, which is the carbon and 2 hydrogens, but we see the fragment of 57 because it has a charge on it. Okay, and then if we lost it as a methyl cation here, we would see that peak as a 15, but we wouldn't see the radical fragment of it. So when we're looking at this, we only see the cations because it's always our fragmentation pattern is always the mass per unit charge we see. Okay, so there's also a splitting in the system up here. If you'll notice, our base ion peak has a 43 and then another peak here, and that this has 2 peaks, specifically a 27 and a 29. Let's look at that little fragmentation here. And the way that we get those kind of things happening to us is that we'll have our major fragment loss will give us our primary mass to charge peak of 43, but it can actually rearrange, eliminate 2 hydrogen radicals and drop it by 2 grams per mole, giving us a more stable allylic cation. So we actually will see some common fragments where they will lose 1 or 2 hydrogens to form a more stable cation fragment that we'll see in that splitting pattern. Okay, so let's get into isotope ratios. Okay, we can actually see the different isotopic ratios in materials right here. Carbon has mostly, if we talk about this as the most common being 100%, we have about 1% of the C13, so we can occasionally see about 1% of our material having that +1 peak, okay? Hydrogen, we have, the deuterium is very, very low percentage, so we rarely see that in mass spectrometry. Nitrogen has a little bit higher concentration of that isotope, which we don't see very much. Oxygen also has a couple isotopes, which we can occasionally see in a concentrated system. Now, once we get to fluorine, we only have 1 stable isotope, so we only ever see 1 peak for that. Silicon has 2 stable isotopes, a +1 isotope and a +2 isotope. And they're in a relative ratio of 5% of the base peak and 3% of the base peak. So we'll see those being a certain fragmentation pattern that we'll see in that mass spectrum. Phosphorus only has 1 stable isotope. Sulfur has 2, but it's less than 1%, so we don't see it very much. Come on, share again. It stopped sharing again. There it is. All right. So when we get to chlorine and bromine, we can actually look at that abundance and tell us that we have chlorine or bromine on the system. For example, chlorine has approximately 2/3 of the species is chlorine 35, but it has about 1/3 that is chlorine 37. So we're going to have a +2 mass peak in that relative ratio of 100 to 30%. And in bromine, we almost have a 1-to-1 ratio between 79 isomer and the 80 isotope. And therefore, we should actually see 2 even peaks when we have bromine on the material. So What this tells us is that it's especially important in things that where we have carbon, nitrogen, and sulfur, or having a chlorine or bromine. We can actually look for those contributions of that mass plus 1 peak or that mass plus 2 peak and identify that we have either sulfur, nitrogen, chlorine, or bromine in our compound just from the mass spectrum. All right, let's take a look at that and what that would look like here. Okay, so if we think about carbon itself and we look at our molecular ion peak, we can see just barely right here, there's a little teeny peak right here at this M+1 peak. Okay, and the relative ratio is approximately 1%, 1.1% of the height of this peak here. Okay, and so we can see it a little bit better if we look at our base peak here. This +1 right here is about 1.1% of that base peak. Okay, so that's really hard to look for if it's only 1%. But let's look at it in the presence of a chlorine or a bromine. What would that look like? Okay, so chlorine has about 75% of it is the 35 isomer and isotope, and 24% of it is approximately the 37 molecular weight isotope. And so what we see here is that we have our M peak plus our M+1 peak, and they're in a ratio of about 3 to 1. Okay, so because these peaks, this molecular ion peak is in a ratio of 3 to 1, we see that there's probably a chlorine in the system because that shows up as that ratio. If we had a bromine in the system, what we'll end up doing is we'll see that we have almost a 1-to-1 peak in the molecular ion peak of the M peak plus the M+2 peak because of the ratios of the bromine 79 and the bromine 81. So we'll see that they have almost a 1-to-1 peak showing up right here in that system. And therefore, we can say definitively, but the mass spectrometry on the one on the left here contains chlorine because of this ratio, and the one on the right here contains bromine because of that ratio. Okay, so then there's also some interesting things we can do with the form of the nitrogen here. Okay, and we have what we call the nitrogen rule. What that states is that hydrocarbons that only contain carbon, hydrogen, and oxygen will always have an even mass. Okay, but the nitrogen rule states that if you have one nitrogen in there, it will have an odd number in that molecular mass. So if we think about that, if you have an odd number of nitrogens in your compound, like 1, 3, or 5, you will have an odd molecular ion peak, okay? Now, if you think about it, if you have two odd number atoms here, and so then you have two of them in there, so an odd times an odd equals an even. So if you have an even number of nitrogens in a compound, you will end up with an even molecular ion peak. So if you have an odd number of odds, you have an odd molecular ion peak. If you have an even number of odds nitrogens, you have an even molecular ion peak. So this is another way to tell whether you have 1, 3, 5, etc. nitrogens in a compound just by the fact that you have an odd molecular ion peak. All right, so now just using mass spectrometry by itself can tell you a lot about the compound, and you can see the fingerprints of using it as a fragmentation pattern to positively identify that particular isomer or that particular compound. But you can also use it on mixtures. And the way we use it on mixtures is when you combine the mass spectrometry with gas chromatography, that you can first separate the materials in the gas chromatography setup and then do mass spec on each of the individual peaks. So not only will you get the relative ratio of the different materials you have in your mixture, you will also have positive identification of each of the individual peaks based on the fragmentation pattern of the mass spectrometry. And that concludes chapter 9.